equation of state, the ideal gas equation of state to come up with the mass of any gas. Okay. Uh, Remember, the only time that we use the ideal gas equation of a state, which is PV equal to nRT or mass over molecular weight RT, is when the question explicitly tells you that's an ideal gas. If the question doesn't tell you what type of gas you have, you need to assume it's a real gas. Okay. And as I said, we can come up with different properties. We can calculate the density of this gas. We know that if the question was exactly the same but find the density, we know the density is mass over volume. So we write again PV is equal to mass over molecular weight RT. Density is mass over volume, so density becomes PM over RT. Pressure is given, M molecular weight for methane. Methane, we know it's alkane. It's CH4, carbon is 12, hydrogen is 1, so the methane molecular weight is 16. So 1000 times 16 divided by R 10.732 and temperature 68 parts 460 to convert it to Rankine, okay, to come up with the density. So we can use this to find the mass, volume, density, specific volume, any other properties of the ideal gas. Okay, here it is. In this example, the question is to assume methane as an ideal gas, find the density at 1000 psi, 68 degree Fahrenheit, and 3.2. As I said, the density is mass over volume, which becomes PM over RT. Pressure is given, molecular weight we know, R 10.732. We need to memorize that, and temperature we convert to Rankine by adding 460. We got 2.83 pound per cubic feet for the density of methane at this condition. Okay. So this was for single component. Like if I have methane, so I can use the molecular weight of methane. If I have ethane, I use the molecular weight of ethane, propane. But what if I have a mixture of multi-components? Okay. So to find that, we are going to use different laws. Okay. The first law that's discussing the mixtures of different gases is the Dalton's law. So what it says, the Dalton says the total pressure, say, the total pressure exerted by a mixture of gases is the equal of the sum of pressures exerted by its components. Okay, this is also known as law of additive pressures. Okay, so pressure exerted by each of the component is known as the partial pressure. If I want to know what is the total pressure is simply the summation of partial pressures. Okay. And this is for ideal gas. And what I can do, I can find the partial pressure of every component in the mixture. So let's say we have a mixture of 3 components, A, B, and C. I can write the equation of a state for component A, component B, and component C and find their partial pressures. For example, for component A, the partial pressure becomes, we know PV is equal to nRT. R is universal gas constant. Temperature is the same for all the components. Volume is the same because that's the volume of the container. So PA is equal to NA times RT divided by V. I can write this for component B and component C. So it becomes, for component B becomes NB, number of moles of component B, times RT over V. And for C the same. And based on the Dalton's law, if I want to have the total pressure, it's the summation of all the partial pressures. So if the total pressure becomes P is equal to PA plus PB plus PC, and in all these, RT over V is constant, so I can factor the RT over V out. So P becomes equal to RT over V times the summation of mole fractions, number of moles. Sorry, the summation of number of moles. So if I have 10 pound mole of methane plus 1 pound mole of ethane plus 2 pound mole of propane, I just sum them up. And then that becomes the total number of moles. So the total number of moles in the mixture is the summation of number of moles of every single component. So pressure becomes P is equal to, again, RTV over N, or PV is equal to nRT. So the equation of a state is still valid if we have the mixture of multiple components. Okay? And here I can rearrange this equation such that I see the partial pressure exerted by any component divided by total pressure becomes equal to the mole fraction of that component. The mole fraction is basically the number of moles of that component divided by total number of moles in the mixture. Remember, the PJ was NJ times RT over V, and P was summation of NJs times RT over V. R universal gas constant was constant, temperature was the system was constant, and the volume was constant. So what it says is basically the mole fraction of every component in the mixture is simply equal to the partial pressure divided by total pressure. Or the partial pressure is equal to the mole fraction of that component times the total pressure. Usually the mole fractions are given. So when we have a sample of the hydrocarbon, we send it to the lab and they are using the gas chromatograph, liquid chromatograph, and they come up with the mole fractions of the gas or liquid in the mixture. Okay, so we will have the mole fractions. We usually show the mole fraction of gas with Y and the mole fraction of liquid with X. So Yj is the mole fraction of component J in the gas phase. So if I want to know what is the partial pressure of that component, that's something that we don't measure in the lab, but we can find it from this equation because the mole fraction can be measured and the total pressure can be measured. So the partial pressure is simply the mole fractions times the total pressure. Okay. This can be written in the same way based on the Amagat's law for the volumes. Okay. So basically, I can just write it the same at a constant temperature and pressure. The total volume becomes the summation of all the volumes. Again, RT over P is constant. Factor it out. You see the equation of a state PV equal to RT, and RT is valid, and is valid, and this should be P. There is a typo here, so it's valid, and from here I can find that the partial volume is also equal to the mole fractions times the total volume. Again, mole fractions comes from the lab. Total volume we know, total pressure we can measure. So I can find the partial volume or partial pressure by simply multiplying the mole fractions times total volume and mole fractions times total pressure. Okay. So what about the molecular weights? So if the partial pressures are the summation of mole fractions, if the partial pressure of the component A is the mole fraction of component A times the total pressure, and the partial volume is mole fractions times the total volume, I can define the apparent molecular weight as well. The apparent molecular weight is simply the weighted average of all the molecular weights based on their mole fraction. Okay, so the apparent molecular weight of mixture is equal to the summation of mole fraction of each component times its molecular weight. Okay. So for example, I can find the apparent molecular weight of air if I know that the air contains nitrogen, oxygen, and argon. And if I send the air sample to the lab and they come back to me saying that 78% is nitrogen, 21% is oxygen, and 1% is argon, I can find some apparent molecular weight for this air, some sort of effective molecular weight. And that's equal to the summation of mole fraction of each component times their molecular weight. The molecular weight of these components, we know them, and it's also given at the end of your book in table A. So the nitrogen has a molecular weight of 28, to be precise 28.01. Oxygen is 32, and argon is 39.94. So mole fractions are given, mole fractions times molecular weights, and we sum them up. So the apparent molecular weight of air is 29. It's a very important number, and we should memorize that. The apparent molecular weight of air is 29 because we use that to define the specific gravity of gas. The specific gravity of gas is defined as apparent molecular weight of gas divided by apparent molecular weight of air, which is 29. Okay? So this is the first property of the gas that we are studying, the specific gravity. It's very important, always reported in the reports, in the samples that they are taking. So you always need to have the specific gravity of gas that you are collecting. And that specific gravity of gas is defined as the apparent molecular weight of gas divided by apparent molecular weight of air, which is 29. How do we get the apparent molecular weight of gas? This is simply equal to the summation of mole fraction of different component of gas in this mixture times their molecular weight. Okay. So here is an example. It says find the specific gravity of typical natural gas. So in this table, the components are given. Okay, so we know in this mixture we have methane, ethane, propane, and N-butane. The mole fractions are also given. This comes from the lab experiment. So we know the components and we know their mole fractions. That's it. The rest we need to come up with. So what is the molecular weight of these components? We either know them or we can read them from the end of the book, table A. For example, methane, I know it's CH4. Carbon is 12, hydrogen is 1, so it's 16. To be precise, it's 16.04. So, but 16 is okay for our purposes as well. But the exact number is 16.04. Or ethane, it's like C2H6. 2 times 12, 24 plus 6, 30. Or to be exact, it's 30.07. Okay, so these numbers are fixed. The molecular weight of each component is fixed, coming from the end of the book. So mole fractions are given, molecular weights are coming from end of the book. You multiply the mole fractions times molecular weights, sum them up. That's the apparent molecular weight of gas, which is 19.26. The question is to find the specific gravity of gas. That becomes the apparent molecular weight of gas divided by apparent molecular weight of air, which is 29. So 19.26 divided by 29 is the specific gravity of gas. Okay. Again, for all these calculations, we are still assuming we have an ideal gas. Okay. So far we understand that the behavior of the ideal gas can be defined with the equation of a state, with the ideal gas equation of a state, which says PV is equal to nRT, or PV is equal to m over molecular weight times RT. If I have a mixture of gases, instead of molecular weight, I'm using apparent molecular weight of gas, because pressure is the total pressure of the system, temperature is total temperature of the system, volume is the volume of the tank, or the total volume of the system. R is constant. So the only thing that I have is the apparent molecular weight, okay, which shows which components we have in the system, okay. And we can use this equation of a state, PV equal to nRT, or PV equal to small m over molecular weight times RT, to calculate different properties of the gases, like a specific gravity, pound of mass, density, specific volume. They all can be calculated through that equation. Okay? But what if we don't have the ideal gas? So what people they did, they tried to correct the ideal gas equation such that it covers the real gas behavior. Okay. So one of the equations that has been used mostly in the oil and gas industry is the compressibility equation of a state. Okay. In the compressibility equation of a state, basically what we are saying is the PV, we are going to use a correction factor, which we call it the Z factor, okay, or compressibility factor, and we change the equation to PV equal to ZnRT. So I'm just adding one Z in front of the right-hand side of the equation. Or if I write it for molecular weight, PVM is equal to ZRT, okay, or density becomes PM over ZRT, okay. For ideal gas, it was PM over RT. Now we have a Z. So what is this Z? This Z factor is a factor which is a function of the gas component. So we have different Z factor for different components. Methane has its own Z factor, ethane has its own Z factor. And this Z factor is also a function of pressure and temperature. So it's a function of component, it's a function of pressure, and it's a function of temperature. Okay? And it's basically defined as the actual volume of the system divided by ideal volume. Remember, in the case of ideal volume, we said the molecules, the gas molecules, they don't take any volume. However, in the actual volume, those molecules will take some volume, and also there is intermolecular forces as well, okay, that basically brings the molecules together or push them away from each other, and then they change the volume, okay. So at very low pressure, very low pressure, you have only few molecules, okay. So at very low pressure, where you have those few molecules, actually their volume is negligible, okay. And since there are only few of them, so the intermolecular forces are negligible. So the actual volume becomes equal to ideal volume. So Z is equal to 1 at a very low pressure, okay. But as pressure increases, it will change, which we'll go over